Okay, well, we can go ahead and get started then. This is the second lecture about process scheduling and the last one that we'll have, because the next lecture on next Monday will be about system calls, because the next Pintos project is about implementing system calls and all of the important things that operating system kernels need to do to protect themselves from misbehaving or maliciously behaving user programs. It's quite a remarkable mechanism because the OS can basically make itself bulletproof. And that's one of the things you'll see in the Pintos write-up is that after this upcoming Pintos project is completed, your OS kernel should be bulletproof against any bad user program behavior. Now we're ignoring things like uh, meltdown inspector, hardware issues that create defects that software can exploit. It's also beyond the scope of this class, although I know Adam has a couple of assignments that explore those things. So that's really cool that you get to have some exposure to them. But we'll dive into the remainder of the process scheduling discussion for today. Let me advance my slide. One thing that we haven't talked about yet is real-time systems. And even if you have a general purpose operating system like Mac OS or Windows 10 or Linux, you have real-time scheduling needs that ought to be served by the operating system kernel because you have media playback, you have video, you have audio playback, and those need to happen on a certain schedule or else it's going to be a very mediocre experience for the user. So real-time scheduling appears in most operating systems, but it's particularly important in certain kinds of systems. You may have a situation where you need to react to a certain input. Anti-lock braking systems are a great example because the system is detecting the spin of the wheel or whether or not, if it's spinning slowly or quickly and so forth. So it's checking on a regular basis to see, is that wheel starting to slip? And if it does, then the software needs to be able to react to that very quickly to prevent a skid. You may have a manufacturing assembly line where the car or whatever it is, the circuit board is going by on the conveyor, and when it reaches a certain point, you detect that with a sensor, and that causes some software to run that places some surface mount chips or puts a weld in space, zap, to weld some pieces of metal together, or something like that. And so you can see that there's a real-time scheduling requirement where we need to have a certain minimum time pass before the software runs. If we exceed some maximum time, then we may have a failure of the actual manufacturing system. So the time between the event occurring and the code taking care of the event, that's called the event latency. And so real-time systems are designed to try to make that event latency as small as possible. Now, even if you can't make it super, super tiny because you're running on a slow processor or whatever, at the very least, knowing that it's consistent is super important. And this is also why these systems tend not to have garbage collection, because garbage collection can occur at unfortunate timings and generate an unexpectedly large latency to responding to certain things. That's also why computer games tend to be written in languages without garbage collectors, because you want every frame to be drawn at a regular interval. And so even if the processor happens to be a slow embedded system processor, as long as the event latency stays bounded or well predicted, then you tend to be able to work with those systems as well. And so like I say on the slide, anti-lock braking, you have 3 to 5 milliseconds to respond to a wheel slide. You got to respond in that time frame, or else bad things start happening to the passengers in the car. Okay, so that's the idea behind real-time scheduling requirements. There's different categories of how important it is to satisfy these real-time requirements. And so you'll see real-time systems divided up into soft real-time and hard real-time. And hard real-time systems require that you hit all of your deadlines. They require that the event, the event gets processed within a certain time frame, because if you exceed it, then a failure occurs. And this is, specifically the examples that I already gave about assembly lines, which may have software running the different stages of assembly, or anti-lock braking. The system is considered to be in a failed state if you miss a deadline. So you cannot miss deadlines, and that's a hard real-time system. That's not what's sitting in front of you right now. What generally is the goal of our general purpose operating systems is soft real-time. We try to hit all our deadlines, but we don't guarantee it. And if we miss a deadline here or there, it isn't considered a failure. So if you think about video playback or video streaming as we have right now, if a frame is missed, if a deadline is missed, you drop a frame, maybe the audio stutters. You've all heard these kinds of things over the last delightful year of remote teaching and so forth. These things happen, and it sucks, but it doesn't cause someone to die or for machines to fail or something like that. So those are soft real-time systems. Now, there are two latencies that you have to think about in real-time scheduling. And one is how long it takes for the interrupt to happen. So some signal goes off, the optical sensor that senses that the circuit board is making its way through the assembly line, and the signal goes high or the signal goes low, and then a hardware interrupt occurs on the system. And then you have the time that the handler actually starts running. Okay, so that's called the interrupt latency. What are we allowed to preempt? That's always the question, right? What interrupts what? And then you have the dispatch latency as well, which is the amount of time it takes from the interrupt handler starting to do its thing to when the process that cares about the event gets to start running. So you have two components here. You have the interrupt latency getting into the handler that knows how to respond to the event, and then how long it takes for the OS to switch over to the process that cares about the event. Those are the two big latencies we care about. So you have your task running, whatever it is, some background operation. Maybe it's a maintenance operation or a logging operation or something like that. And then the interrupt occurs and stuff is happening, right? You can't deliver an interrupt in the middle of an instruction, because that's not how processors work. You have to wait for an instruction to finish, and then you can deliver interrupts, and then the next instruction can start executing. So the current instruction has to finish. If interrupts are off because you're in some kind of critical section that you need to protect from interrupt handlers, then that'll happen after you turn interrupts back on. Okay, so then the CPU is going to dispatch to the interrupt handler. And then, of course, inside the interrupt handler, we need to save some limited machine context so that the interrupt handler can be written in a language, a high-level language like C. You probably won't hear that phrase in any other class, but in OS, it is a high-level language compared to assembly. And then you save the process context that was interrupted, and you figure out what process to switch to, and off you go to the races. Okay. And yeah, so you can see here that this, time from the interrupt, let's say the hardware event occurring, to the time that the interrupt service routine can start responding, that's a certain amount of time. We got to make that small and hopefully bounded. I talk about this on a subsequent slide, but you can imagine that one of the consequences of this picture is, if we do need to turn off interrupts for critical sections, we should try to keep critical sections as tiny as possible so that as little gets in the way of us getting to the ISR as possible. ISR meaning the interrupt service routine. Okay, now, so this is just what I was saying. You want to try to keep your critical sections small in these kinds of real-time systems. Another aspect of this that allows you to minimize your interrupt latency is whether or not you're allowed to interrupt other kernel control paths. So if you're in a trap handler for a low priority process and a real-time event goes off, you'd like to be able to interrupt the kernel trap handler for the sake of the interrupt service. Okay, so this is a situation where preemptible kernels, or kernel preemption is the way that we generally describe it, is really helpful in a real-time system to get that interrupt latency down as small as possible. Okay, now here's a little bit more of a picture. You can see the picture from before. You have your interrupt latency, and so you have these various things that you're doing to get into the interrupt service routine. I suppose that I should be careful because if you go back a few slides, I want you to notice where I drew this line in particular. So the interrupt latency ends at the end of the interrupt service routine, and that's not the way I represented it on this earlier slide, because you can see the interrupt latency goes to the beginning of the ISR. So anyway, you know, inconsistencies notwithstanding, once you get into the interrupt service routine, now you need to get to the real-time process that actually cares about this. And so you want to, again, make sure that your dispatcher or your task switcher is as efficient as possible. So you just figure out the minimal set of instructions to restore the machine context of the real-time process. Okay, and there's a couple of other things as well, because you could imagine that switching to the the process that cares about this, do you invoke the scheduler or not? Well, if you have a hard-coded real-time system, you probably know exactly what process to switch to. Otherwise, it may just be that the scheduler runs and it picks a process to run who's unblocked. And so that would suggest that the real-time process should be at a very high priority so that it gets to preempt anybody else that comes in its way. And so that's what you generally notice with general purpose OSs like Windows, Linux, and Mac OS, is that real-time processes occupy a special range of priorities that are higher than any other priority of any other process in the system. Like Windows, you can, if you bring up the task manager, don't do this right now because it may cause things to crash for you, but you can bring up the task manager and go in and set the priorities of the running processes. And I remember as a youth, I would go and tinker with Windows and set the process that responds to the mouse at a very low priority, and the system becomes unusable. Something like that, you want to have it a very high priority because you want the system to be responsive to the user. Okay. Yeah, the second implication is one we've already talked about. We want to make sure that if a high priority real-time process becomes unblocked because some event has occurred, we need to make sure that any lower priority process is kicked off the CPU immediately. Like, we don't allow them to finish their time slice. We don't wait for them to block. We just kick them off so that the real-time process can respond to the event. So these are the main implications of how real-time OSs work with process scheduling. Okay, yeah, so I already talked about this. The dispatcher needs to be as efficient as possible. And another issue that you run into, you might notice there's like this magic empty box, and why would that be empty right now? Sometimes it occurs that a lower priority process may be holding resources that a real-time process needs. And so there is a little gap in this mechanism for resolving those kinds of conflicts where a real-time process needs some resources that a lower priority process is holding. And so it may be really simple. It may be that general purpose operating systems don't have this kind of problem because they don't allow processes to share resources in this way. But in cases where there are resources that processes can hold on to, the real-time process needs to get those resources so that it can interact with them. So like I say here, the resource conflict phase also may need to occur in certain kinds of real-time operating systems, okay? All of this is the stuff that has to happen. Okay. Now, what happens over here, you can see this line is obviously correct, where it comes down. Once we dispatch to the real-time process, now we have the process responding to whatever the event was. So we had whatever was running before, some event occurs, some generally physical external device goes off, and then we have our event latency, and then the real-time process can start running. And we want this to be small, but more importantly, we want it to be consistent so that we can actually plan around it. Okay. There's a couple of approaches to scheduling processes, because what you notice is that real-time processes are often periodic. They need to get on the CPU at specific intervals. Okay. If you're doing media playback, that's an obvious example. If you're an anti-lock braking system, obvious example, because you want to check on the wheel state I think it's like 20 times a second. So what is that? Like is it 50 milliseconds? I'd have to go do some math, but I think it's 50 milliseconds. Every 50 milliseconds, you'd want to check on the wheels, make sure that nothing has started to spin or lock. So you have these kinds of periodic scheduling requirements. And so we say that the process requires a specific period. So period P, that's the time interval that we need to be scheduled on. And of course, the real-time process is going to have a CPU burst of a certain length. And that obviously needs to be smaller than the period. Otherwise, there's no way we can schedule this. Okay. A lot of times it's a very small period. I'm sorry, a very small CPU burst for the time t. And so you can see that taking these two values, we have a window. Anytime in that window, our process can run. We need to give it the CPU somewhere within that window. So we could start it right away at the beginning of the period, and then it can run really quickly, and then we have tons of time because we know we're not going to miss our deadline. Or we could take at least this much time, start the process running, and then we know it'll finish before its deadline. So this deadline D, this is sort of denoting a window that we have in which we must schedule that process to run. Okay? That'll become important because when I show you some examples of scheduling algorithms, you'll see that I talk about it as a window. It's not like you have to execute it right at this point. You can go anytime from the start of the period all the way to this deadline. And then if it's after, you missed. Okay, let's see. Yeah, one simple way of dealing with this is just having processes tell you, I need the CPU every 50 milliseconds. And that makes sense, right? Because the hardware timer interrupt handler is going to need to know about that so that it, the scheduler can take care of it. So there are situations where it makes a lot of sense for the OS to just be informed. There's some things the OS scheduler just doesn't know. It's easiest to just inform it. Okay. Now, if the process says this is what my need is, it gives the OS a chance to say, sorry, there's no way I can do that for you. And so that is an example of an admission control algorithm where you're actually giving the OS the power to say, no, I'm not going to even allow the scheduling request because there's just no way that I can do it successfully. Okay. And so like a hard real-time operating system would use an admission control mechanism because a hard real-time OS can't start failing everybody else because a given process has unrealistic expectations. And certainly if that process's expectations can't be met, then the OS should inform it as well. So hard real-time systems tend to be very strict about admitting scheduling requests and scheduling requirements. Okay, a simple scheduling algorithm is called rate monotonic. It's a very simple algorithm because basically it's a priority-based scheduling mechanism. The shorter your period, the higher your priority. So if you have a long period, then you have a very low priority. And if you have a teeny tiny period, then your priority is very high. Okay, so simple mechanism, you would think. rate monotonic scheduling is a pretty easy algorithm to implement. Oh yeah, and as I say here on the slide, this mechanism includes preemption. So if a low priority process is running and then a high priority process gets into its little deadline window, it preempts the lower priority real-time process. And this algorithm is optimal as long as you're talking only about real-time scheduling algorithms that statically impose priorities. So the priority of a process doesn't change over time. And because of that, there are certain limitations that I think are fascinating about this algorithm. Okay, so here's a simple example. Lower priority processes can be preempted by higher priority ones. It is possible to have priority inversion because everybody's got fixed priorities, and you lock something as a low priority process and a high priority process needs it. Now you have a problem. But the solutions are all the same as what we've already discussed. The question that is interesting about this algorithm is it possible necessarily to schedule a set of processes with real-time scheduling requirements? Okay, and we're going to use the same parameters as before. We need the CPU on a certain time period, P, and we only expect to consume a certain CPU burst length, T. Okay, and we're going to pretend that nothing changes and it's perfect every time. It always stays within T. So let's say we have these two real-time processes. P1 has a period of 50 clocks, CPU burst of 20 clocks. Now you could say, well, okay, 50 clocks, 20 clocks. That's it's using 20 clocks out of 50, so that's 40% of the CPU's available time. P2 has a period of 100 clocks and a CPU burst time of 35 clocks, so that's 35% of the CPU time. So 40 plus 35 is 75%. We'd expect this to be schedulable. So these are the completion times, and using the burst times, you can use that to figure out whether or not it's possible to hit your deadlines. So P1 and P2 can start executing at time 0 because they're both inside their window, but they have different priorities. P1 has a shorter period, so it's got a higher priority. Okay, so P1 goes first, and it runs, and it's got a CPU burst of 20 clocks, so it finishes, and then P2 can start to run. Now you'll notice that P2 only gets to run for 30 clocks, but its CPU burst length is 35 clocks. So it still has 5 clocks worth of work to do when P1 enters its next window. And P1 is at higher priority, so it preempts P2. So P1 jumps on the CPU, takes over, and again finishes a CPU burst of 20 clocks. Then P2 finishes the 5 clocks of remaining work that it has, and then we're done. And we get to the next window, P1 runs, and you basically see this kind of pattern repeat. Okay, everybody got that? That's rate monotonic scheduling. So the question is, oh yeah, so this is basically what I was talking about before. If we look at these and say, well, you're using 20 out of 50 clocks, you're using 35 out of 100 clocks. That concept is called CPU utilization. What percentage of the available CPU time is being used? And so you can see here that the total CPU utilization is 0.75. And I think an obvious question arises, can we actually use this measure to tell if a set of real-time processes can actually be scheduled using rate monotonic scheduling? And so here's another example. We have 50 clocks, so P1 is a period of 50 clocks. It'll have the higher priority, CPU burst of 25 clocks, so its utilization is 50%. And then we have P2 with a period of 80 clocks and a CPU burst of 35 clocks. Now that's clearly less than 50% CPU utilization. So the overall CPU utilization is under 100%. So is it schedulable? This is the question. Okay. So yeah, here's the math. P2 is around 44%. So that's 94% CPU utilization. We'd expect 6 clocks out of every 100 to be available to do other things. At least that's the idea. If we can use CPU utilization to predict whether or not we can meet all of our scheduling requirements. Okay, so let's play this out. P1 has a shorter period, so it starts running first, because both P1 and P2 could start running right at the very beginning. And so it runs for 25 clocks and finishes. Then P2 starts running, and remember, it was, what do I remember? 35 clocks out of 80 is what it needs. So it runs for 25 clocks, and then we enter the next window for P1. And P1 is shorter period, so it preempts P2, and it starts running. And again, P1 gets 25 clocks. Now, sadly, we have 5 clocks left over before P2's deadline hits. We have done 25 clocks worth of work. We need to complete 10 more clocks, but we only have 5 clocks before P2's deadline hits. So you can see that it misses its deadline by 5 clocks. So this is a really strange result. The CPU utilization is less than 100%, but we can't schedule these processes using rate monotonic scheduling. Okay. It turns out that some smart people whose names I have on the slide figured out what the requirements were for scheduling n real-time processes using rate monotonic scheduling. Okay, and so you can see what the maximum CPU utilization limit is here. Okay, I might mention that Liu was at MIT and Leyland was at JPL. So I'm 99% certain this was being explored for spacecraft using real-time scheduling algorithms and what constraints the software had to operate within for this to work properly. So pretty fascinating. You can see that the CPU utilization limit is pretty low. So are there other ways? And the answer is yes. In fact, the most popular way that this is done is called earliest deadline first. Earliest deadline first scheduling dynamically modifies the process priorities based on whose deadline is closest. I think I like to say this is also the college student scheduling algorithm because basically what you're thinking about is which deadline am I most likely to miss? That's the thing that I'm going to work on first. And then you tune your focus over time based on which deadline you're most concerned about missing. I'll be honest, I do that too. So, but earliest deadline first will dynamically change the priorities of real-time processes based on where the deadlines are and how in danger the process is of missing the deadline. Okay, so we had this example. This was the example that broke rate monotonic scheduling. And we know that the CPU utilization is under 100%. It's 94%. Now, instead of looking at the period length and determining the priority from the period length, now we look at the next deadline we have to hit to figure out who is the highest priority and who should get the CPU. So let's look at how this unfolds. Okay. Now, as before, we have P1 and P2 can both run, but P1's deadline is closer. So P1 has the higher priority. And so it runs and it finishes. Then we get into a situation where P2 starts running. And remember, its burst length was 35 clocks. And so it has run for 25 clocks. We enter another window for P1. And you can see where P1's next deadline is. It's after P2's deadline. So in this case, P2 is higher priority than P1. So P2 continues running until it's finished. Then we can go ahead and start running P1. Okay, so these are the next deadlines for P1 and P2. P1's deadline is clearly closer, so it runs and it completes. And then we can go ahead and start running P2. But you'll notice here, so P2 is at 80 and 160, and the next one would be 240. P1s would be 50, 100, and the next one is at 150. 150 is before 160. So at the point that we enter the next window for P1, its deadline is closer than P2's deadline, so it now preempts P2. Okay? So P1 completes, and fortunately, we still have plenty of time to finish off P2, so P2 gets done, and everybody's happy. So you can see that as this unfolds, both processes are continually meeting their deadlines. This is a great result. We have a little bit of time left over that we're happy. And of course, when we hit this next point, P1, we'll enter the next window for P1. P1 will start executing again, and the system just unfolds. Okay. So earliest deadline first scheduling is quite an interesting algorithm. It actually has fewer requirements than rate monotonic scheduling. You might have noticed I mentioned it on an earlier slide, but I didn't really make a big deal out of it. All we really need processes to do is say when they need the CPU next. We don't even need them to be periodic processes. And we don't need them to, maybe they need it on varying intervals. Maybe they need it just for one-off, AKA one-shot events. Okay. So as long as the process says when it needs the operating system to switch to it, the kernel can schedule that. Obviously, you also need to know the burst length so you can see if it's even feasible. But this is pretty dang cool. Earliest deadline first is a great scheduling algorithm. Also, you'll notice that I say on the slide, it is theoretically optimal, which means if in a world with massless, frictionless pulleys and massless springs and all of these kinds of things that we have in nice early physics classes, we also have CPUs with zero internet dispatch latency and zero event latency. Earliest deadline first could actually reach 100% CPU utilization for real-time processes. So if the CPU utilization is under 100%, or let's say 100 or less, no problem. EDF can schedule it. Now, since you do have latencies in the system, you can't reach that 100% CPU utilization because you're always going to lose a little bit. And since that's on a per process basis, if you had 10 processes that each were 10% CPU utilization versus 100 processes with 1% CPU utilization, one of those is worse than the other. So it kind of really depends on the situation you're talking about. But it is theoretically optimal, which is pretty dang cool. Okay, any questions about real-time scheduling? Because that is about all we're going to say about real-time scheduling. The last thing that I want to talk about today, if you have any questions, feel free to plop them in chat or just interrupt me. But the last thing that I want to talk about is the Linux schedulers, because Linux has been doing its own thing since Linux 2.4, and that's kind of interesting. I mentioned last time that Linux up until 2.4 kernel would use multi-level feedback queues. That's what Linux would use. A very common standard approach used widely across most operating systems. Linux 2.4 started doing something else. And basically the execution time of the CPU was divided into epochs, which were just chunks of large scale chunks of time is really all an epoch is. And at the beginning of the epoch, all the processes in the system would be prioritized based on previous behavior. Okay, so if you had a real-time process, then that would have a very high priority and it would be fixed because it's a real-time process. And by virtue of being real-time, you're assuming that it needs to get the CPU very quickly. So you have a higher priority band than everybody else, and it's fixed. Otherwise, if you block or yield quickly and frequently, then you're given a high priority. And if you get preempted frequently, you get a low priority. And so the scheduler would assign a priority to every process at the beginning of each epoch. And besides getting a priority, each process would also get a time slice, aka a time quantum. And so this would basically say, this is how much time you get to stay on the processor during this epoch. So that's the idea. Of course, you can yield, and if you yield, then you still have some time left over, which other processes may run, and then you get the CPU again, you use up more of your quantum, and then you yield again. You could block and then become unblocked during the same epoch, and you get to go back and use up more of your time quantum, and then maybe you block again. So all these things are going on, but you have this time quantum that's slowly shrinking, and every process that's running, their time quantum is shrinking as they use it up. Okay, so the scheduler is invoked, it runs over all the processes, and it basically scores processes based on a few considerations. One is its priority, but that's not the only thing. An interesting thing about the 2.4 scheduler is it would give like 15 extra points to any process that was on the same CPU that it's trying to schedule for, because the presumption is that process may still have some data in cache, and by running that process again on the same CPU will be more efficient. Okay, and so you score all the processes, and whichever one comes out on top of the scoring, that one gets the CPU. Okay. Now, you might look at this and say, well, that seems like problematic or potentially problematic. Just remember that time quantum is shrinking, and once it shrinks to 0, that process is no longer in the running. So it won't get scored and selected for a CPU at the point that its time quantum is run out. If it's blocked on some long running, task in the background, it's not considered. So it's only the ready to run processes that have available time quantum that are scored in this mechanism. Okay, higher priority processes preempt lower priority ones. So if some high priority process gets unblocked and it still has time quantum left, then it gets a CPU. And the epoch ends when all the processes have consumed all of their time quantum. Okay. As one would expect. Okay, so this is just reiterating something I've already said. Now, let me see what I say about this. Yeah, so once you have finished the epoch, so you've used up, everybody's used up all their time quanta, or they're blocked, or they've terminated, or whatever, then the scheduler does this whole mechanism again. It iterates through all the processes, assigns priorities based on the things I already discussed. Everybody gets a time quantum, and you do it again. Okay. Now, there are a number of issues with this. There's some really obvious issues, and then maybe some less obvious issues. One of the obvious issues is that this scales terribly because you're doing a lot of running through all the processes and looking at them. You remember, if you're scoring processes in the scheduler, like who's the best, you're the best, you get to have a CPU. At the end of the epoch, you run through all of the processes. This scales really badly with an increasing number of processes, okay? And so the Linux 2.6 scheduler took this mechanism and re-implemented it to be as efficient as possible. Now there's a second issue. Like I say here, it captured the 2.6 scheduler captured the same principles of the 2.4 scheduler. One of the other issues is think about how many little knobs and dials there are in this scheduler. Well, what range of time quanta do I assign? What's the minimum time quantum? What's the maximum time quantum? How do I map process priority to time quantum? All of those kinds of questions. And so this scheduler was really difficult to tune, and this is one of the things that people ran into frequently, is it was really easy to change one little knob in the scheduler and suddenly it behaved terribly. So that was a major issue that people had with the 2.4 scheduler. So let me see what the question is in chat. In the multi-level feedback queue, higher priority processes get shorter time slices. No, actually it should be that the higher priority processes get a longer time slice. in multi-level feedback? I'm trying to think. Oh yeah, I'm sorry. You're correct. The reason why, first of all, the Linux scheduler is just trying to be nice to high priority processes. It's just making sure that they get the CPU whenever they want it. And that's the kind of the big reason why the 2.4 scheduler would give a large time slice to high priority processes. The reason why multi-level feedback queues have a small time slice for high priority processes is, remember that the multi-level feedback queue does two things at once. Besides prioritizing the processes, it's also categorizing them based on their behavior. And so we have a small time slice so that we can identify processes that are more toward the compute intensive end. So we have a small time slice, process gets preempted, it gets bumped down. Oh, it gets preempted again, it gets bumped down. So that would be probably the primary reason why you see a difference between the way that this scheduler works and multi-level feedback queue schedulers work, because this scheduler is using other things to validate behavior. Multi-level feedback queue is using preemption to figure out how to schedule processes. So that would be the primary reason why. That's an excellent question. Any other questions? Cool. All right. Well, if anybody thinks of one, feel free to plop it in. So you have, I love this name, the O1 scheduler. This is the same approach generally as the 2.4 scheduler, but it's just written in a way that is very efficient. So you have a priority array. Some of you have constructed something like this in your kernels. I've gotten to see a couple of the implementations in office hours, and you have something like this where you have multiple queues. They call it a priority array, and each priority level just has a queue of the processes at that priority level. And there's a bitmap that records whether or not there's a process at that priority level. And the idea is that since there is a fixed number of priority levels, checking to see which priority queue to take a process from is a constant time operation. This is where the O1 comes from, okay? So finding the highest priority process to run is a constant time operation. We just find the index of the lowest one bit in the bitmap, which turns out you can do with a bitwise and a subtract operation. So just a few instructions, the CPU can do that very fast, and you can use that index to access the priority array. Okay, so the O1 scheduler has two priority arrays. One is for the current epoch, and one is for the next epoch. Remember that part of the 2.4 scheduler's idea or approach was that if there's any process with remaining time quantum left, it gets to have the CPU. And so the active priority array will have processes in it if any process has time quantum left. Once it runs out, it gets moved to the next array. Okay? And in the process of being moved to the other array, its priority is also recalculated. So you can see that maybe things move. That second high priority process stays at the same priority level. That guy jumped down a couple, that one stayed at the same level, and that one also stayed at the same level. So this is going on incrementally, which is, has a lot less of this like really gross scaling issues than the 2.4 scheduler had with increasing numbers of processes. Okay. When the active priority array becomes empty, so all of those bits in the bitmap become 0, you're done with the current epoch. You swap the pointers between the expired and the active arrays, and you go again. And so that was the premise behind the O1 scheduler. It's a pretty straightforward mechanism, and just super fast. And so that thing stuck around for a while, but you'll notice that it didn't last very long. And part of the reason why is it still had as many knobs as the 2.4 scheduler, and it was still difficult to tune. I remember a lot of discussion about this. There were some pretty heated discussions about this on some of the Linux kernel mailing lists about people making tweaks and it just messing everything up in how processes were scheduled. So after 2.6.23, Linux switched to another scheduler, which again has a wonderful name, the Completely Fair Scheduler. Who wouldn't want a completely fair scheduler? So I just love the names of these things. The Completely Fair Scheduler is based on a completely different idea that basically has just one or two knobs that you can adjust, and it achieves some very rich scheduling behavior. So what the Completely Fair Scheduler is focused on is making sure that processes get a quote-unquote fair share of the CPU, okay? Now, the fair share should be dictated by the priority. The higher the priority, the more likely it should be that that process gets onto the CPU, okay? So it gets a larger share if it needs it. Of course, if it takes a larger share, it's going to start being demoted in priority, and that'll change things. So it's a very interesting system in how it tunes itself to process behavior. So every process has this thing called the virtual runtime of that process. You might remember that we can record as the kernel, we know everything. We can record how long the process has been on the CPU. So, but this is a virtual runtime. We actually scale how long it's been on the CPU by its priority. And so basically you can think of this as every process having a clock, and the clock runs slower if the process is higher priority. So just automatically by doing that, higher priority processes have a slower running clock. They end up looking like they've been on the CPU less, and so they're more likely to get the CPU quickly if they become ready to run. It's a crazy approach, but I love it. It's one of these alternate scheduling mechanisms that's just really interesting to tinker with. So all of the ready processes are maintained in a balanced tree that's ordered by increasing virtual runtime. So the ones that have the lowest virtual clock value are going to be leftmost. They're the ones that appear to have been on the CPU the least. It may just be that it's a very high priority and its clock runs really slowly. And so it's the one that gets the CPU. The leftmost process is the one that gets the CPU when the scheduler needs to make a decision. Now, part of this is that the scheduler maintains a record of who is the leftmost process. And so getting the next process to run is always a constant time operation. So that part is constant time. Obviously, putting stuff into the tree is a log time operation. So the Completely Fair Scheduler is going to choose a time quantum based on a few things: targeted latency of the system. So we need to make sure that every ready process gets the CPU at least once within a certain window. And so the targeted latency, the window is going to be some absolute measure. So that would affect the amount of time we should let each process sit on the processor. And of course, the total number of processes in the system will affect this as well. Okay. And as it says on the slide, you can increase the targeted latency if you need to, because there's many processes running or lots of high priority processes or something like that. And so the scheduler makes these dynamic decisions about when to preempt the current process and move it back into the ready queue and let somebody else have a go. So it's a really remarkable scheduling approach. And as it says on the slide, processes that block or yield frequently, they have lower virtual runtimes. So when they become ready to run, they get the processor quickly. Okay, so that's a pretty interesting result. There's no certainty as to how long Linux will stick with this scheduler. I love Linux because people are very experimental in it. Commercial operating systems have to be a lot more conservative because customers will get really grumpy and that'll affect revenues. But with an OS like Linux, where you can just switch the scheduler based on the system's needs, or there's a lot of people using it, experimenting with it, you have a lot more flexibility to try new things. And so that's one of the things I love about Linux, is that it gives you this chance to try other things. Now, I want to mention a couple of other algorithms. If you really like this stuff, do yourself a favor and look up this paper, Lottery and Stride Scheduling, because there are a couple of techniques in here that are completely different from anything we've really talked about. The completely fair scheduler is kind of an implementation of this technique called stride scheduling, which is based on this notion of processes having virtual clocks that are affected by their priority. Okay, so there's another one. Lottery scheduling is great because basically, based on a process's priorities, you give each process a number of lottery tickets, and then you hold a lottery to see who gets the CPU next. It's a really interesting approach. So read that paper if you're interested in this kind of thing. There's a lot of fun experimental approaches that one can try out. Don't do this for Pintos though, probably. Okay, that's all we have to talk about this time. As I mentioned at the beginning, on Friday, we won't have CS124 class because it's a student faculty conference, and I will be attending, and I want to encourage you to attend, or you can work on your 124 assignment, or do both. I'll probably be doing other stuff too while I listen. But when we come back to CS124 on Monday, we'll start talking about how user space works, how we maintain the separation, and how we build system calls so that kernels can never be knocked over by a misbehaving process. If anybody has any questions, feel free to hang out. Otherwise, I will see you on Monday.